Hi everybody, welcome back to Climate Change Calculated, this time a Corona update number 4, or the power of modeling and estimations using Python and Jupyter Notebooks. If you're interested, stay tuned. So why Climate Change Calculated? But first, you can read the slides here using this link. So these slides are in GitHub, and you can let them run on Google Colab, as I do here. And basically, you can see the same slides with the same functionality, which we will see. So what's the connection to climate change? Well, climate change causes shifts in habitats of animals and plants, and this in turn leads to new contacts and encounters between animals and humans. And this in turn leads to increased opportunities for viruses to jump between species. For instance, like bats, which are thought to be the origin of the coronaviruses. And this is the origin of new and dangerous viruses and pandemics, right? So if you have new variants of viruses, then our immune system doesn't know how to fight it, and that makes them dangerous. So the goal here would be planability and certainty through modeling and data analysis, which I will show here. And then safety through seeing the effectiveness of measures, like checking which measure does what, which we will also see. So these are the highlights of this presentation. It compares different countries internationally, so it's always good to have a comparison to see what can be improved. Then it shows time plots, which show trends and developments over time for predictions, and also to see how measures work. And it uses models as comparison and for predictions. So this is always important for orientation. Is this what you expect? And it bases all on this database from the Johns-Hopkins University, which has an online GitHub repository, right? And this is updated daily, and I will use this GitHub repository from the Johns-Hopkins University for my plots in the following. But as with every measurement, there's only limited accuracy to the data. So this is something you need to keep in mind. That's the estimation part, right? Data is always imprecise. For instance, by delayed notifications. And comparing the Johns-Hopkins University data with data from the Robert Koch Institute in Germany shows an accuracy of about 1%. So that's how much they differ. And this is actually much better than we need for our purposes. So 1% is actually quite good. So that leads us to the first topic here, the comparison of the infection risk in different countries. So this is particularly interesting if you want to travel, for instance, which is difficult in pandemics, but it's still kind of interesting to compare different countries in this respect. So only people who are infected but did not yet recover or die are infectious, right? It's kind of logical. These are the concurrently or active sick. The number of concurrently sick is the number of infected minus the number of recovered and death. So this simple formula. So you have the concurrently sick, which is the total number of infected, so the cumulative number, minus the recovered, minus the total number of death. So to compute it, we first need to choose the countries, and for that I made those pull-down menus, which you can use to select countries to compute and display in the following. And you can also select empty for no country if you want to limit the number of plots. So there you can also select the start date, which is down here, for the computations. So here I chose the 1st of March, where basically everything began. Also, you can limit the display using the zoom tools in the plots that we will see. And after selecting the countries here, you need to run runtime run all or control F9. right? So this is something that you can actually see here. Here I have runtime, and then here you have run all, and this lets you run everything. Yeah, so here I have pre-selected some countries, but you can also change them here in this pull-down menu. You have several to choose from, and you also have this empty choice. Yeah, so now we are done with the selection of the countries for comparison. We have a time span from March 1st to today, which is mid-February, and then we can analyze it. So for that, I'm using interactive plots. So they have a zoom tool, which is activated by bringing the mouse to the upper right side of the plot. And we have a panning tool, which lets us shift the selection and also reset, going back to the original setting. So here's the first one. And here you can also see a warning. There is a problem with the data consistency for Spain, France, and the US, because they don't really have consistent numbers for the recovered, right? So particularly the US stopped giving the recovered data like a month ago. So instead I'm using the 16-day incidence. So I'm assuming that after testing positive, after 16 days, the person is either recovered or dead, right? So that's the estimation. And actually in my first corona video, I showed that the 16 is a reasonable number. Yeah, so here you can see it. Here are the plots, and you can see the top plot here is the US. And yeah, that's partially because it has the largest population of my selection, but also because they have much higher infection rate, as you will see when we normalize this to per million inhabitants. Right. And you can also see we have the zoom tool here, which is activated now. And for instance, we can zoom in here for the part of Germany. Here we can see the spring peak, and here's now the fall peak. So I can also pan using this crosshairs here, and we can see here there's this peak for Germany and around Christmas. So there's this fall peak around Christmas for Germany, and we can also see that it's much higher than the spring peak was. We can also see that there is a similar behavior for the other countries. Like they all had the spring peak, but the US didn't really go down. It just had a peak, another peak in summer, then third peak here in fall and winter. And Italy is quite high. France is also quite high. Spain is very high later. Yeah, but it's yeah, and this is now the first where we apply a model, the modeling. So the virus spread is actually quite easily modeled by this logistic model, right, which I already showed here in my Corona special, the first Corona video. And here's this logistic function. So here we have r, this r here in the exponent is the logarithm of the factor of increase, where this is the factor from day to day. So that's basically the factor of increase of the infected from day to day. Then k is the carrying capacity. In the case of Germany, this would be 83 million or 83E6 in scientific notation. Then P0 is the number of cases at the starting date, t equals 0. And t is the number of days. And for modeling the number of concurrently sick, CS of t, I used the time from infection to recovery or death of 16 days, which we just saw, and computed the difference, right? P of t minus P of t minus 16. So this difference is the number of concurrently infected. And then in this video from March, this very early video, I've already found a scenario which I called a possible solution, because that looks like a possible solution, like the name says. And I found if we have a factor of 1.02 for this factor of increase, then we can delay the main peak until spring 2021. And in my optimistic scenario, that's where vaccine would be available, which fortunately is the case now in 2021. So it's kind of like the happy end now that we indeed have vaccines, although it's kind of going slowly, but we have them. That's the important part. So here's now the comparison between my model and the actual data. So here we have the concurrently sick of Germany from the data, and then the comparison with my model from March, my possible solution model. And here we can see that Germany stayed more or less close to this model, and this model can be seen as a target to reach by the measures. So here you can see it. Here in blue you can see my logistic model starting here on March 1st. Here we can see the spring peak going up to 70,000 concurrently sick in Germany. Then we had the measures, lockdown and mask wearing, and it went down quite nicely. So here we have May. So in May the lockdown was ended and we had just mask wearing, and it almost worked as well. And here in the summertime it stayed low. Then it increased somewhat during vacation time, September, and then all of a sudden in October there's a steep increase. So we can see it actually now becomes more distant to the model. So here it followed my model quite nicely. Then all of a sudden here in early October it deviates a lot. So it becomes much steeper. So this was the time when people went back indoors, so there was more infection possibilities, and also that's the time when all the corona denier demonstrations happened, where they were close together without masks and basically ignoring all the safety measures, and were traveling together in buses and then going back to their home places and possibly spreading more viruses. So they all contributed to the spread of the virus more evenly across the country. So as a consequence, we have a steep increase here in corona cases until we have this second lockdown here in November, this soft lockdown, which didn't really help so much. Then here it was flattening somewhat, and here we had a more strict lockdown, which didn't really help until about Christmas. And then after Christmas you could see the effect. So it really went down quite sharply again, similar to the springtime. So here we see the effect of the measures, lockdown and mask wearing and keeping the distance. Same here. So we have a steep decline, and this looks like a data problem here. It seems here that we have delayed data, so it's like an artifact, so it should go down like continuously like we have now. So here now we have the latest data from February 13th, and you can see it actually reaches my model now. So that means it's kind of this is where we want to be. We want to be close to the model, because that leads us to the solution that we keep it more or less down to values that can be handled. And when we have vaccines, which is at some point this year, then we will be done with it. So this kind of, to me, looks like a happy end. So that's a good thing. So I'm curious how it will continue, if we manage to go further down below my model. Because you can see here the model has a quite steep increase, which we don't really want to see. And it has this steep increase because the virus at this stage is quite evenly distributed in the country, in the population, and That means if we have if the condition for the virus becomes more favorable, it will quickly increase. Or if we have a variant like the British variant, which is more infectious, that creates also better conditions for the virus. And then again, it will increase more sharply. So that's actually kind of also a critical point here. So we need to watch out for keeping the condition for the virus unfavorable. Yeah, here I have sonification, where you can actually hear the plots. I use two tones. One tone for the actual data, so louder means higher values, and the other tone for my logistic model. So let's try it. Yeah, so the lower pitch tone is my model, and the higher pitch tone is the actual data. Yeah, so it's just basically a different way of presenting the data. Yeah, and to compare data between different countries, it makes sense to normalize them to the number of inhabitants, right? To have the concurrently sick per million inhabitants. In this way, we can compare different countries and get something like a measure of infectiousness of different countries. You know what fraction of people are infectious. And this is what we can see here in this plot. Here I plot the concurrently sick per million inhabitants. So now we can compare how successful different countries are in combating the virus. Here orange is again Germany. You can see here, and we can zoom in again here in spring. We were quite successful here. In April going down again, and then here going up. And I can pan and see here. Here's again the top, the fall top. On Christmas Day, 4,589 per million. But you can see actually other countries are far worse. So here's our peak. And then we can compare it to the US about the same time. They have more than twice as many. So here 4,500 for Germany. The US has over 10,000 per million. So the US is much worse. And you can actually see that from the beginning. Here up until the peak in the spring, the US was or just before the peak, the US was similar, but then it was just going up and up, only slightly down here in the summer, then going up again, slightly down, and then up a lot. Up until the beginning of January, and maybe that has to do with a new government that they now have. So now maybe, hopefully, they start to take it seriously and apply the measures, which we also applied successfully in Germany. And here you can see actually it's also going down steeply. So the same measures that worked in Germany also now work in the US. So that is good. Kind of interesting here is this curve of Portugal, right? It's even, they have a very steep increase, even more than the US. And that can be explained with this British variant, it seems, that is more infectious, and so it creates itself better conditions for spreading. But again, here also in Portugal, those measures work, right? They have the same measures, lockdown, mask wearing, distance, and they work to decrease the number of infected. Yeah, Italy is another country which has a very, very high peak, again also going down a lot here. Then we have France, almost as high as Italy. So France had a very steep increase, and then around November, beginning of November, it also has a steep decrease. So this also shows a lot of success. So they had a very strict lockdown in France, and that actually also helped a lot, which you can see here. But then also they start to increase. So then they loosened the lockdown, and now they have begin to increase again. So that actually shows quite nicely the effectiveness of the measures, looking at these time plots. Yeah, this can also be seen in this following plot, where you have a zoom in to the March peak. So here you can see the curve of Germany. Here in the end of March, we have the start of Germany's corona restrictions, and we can see about a week later we have a decline in the new infections. So it takes about a week until we see it. I would say at least a week. And you can also see here that the US was just continuing to rise and flattened a little bit and then was rising again. Here Spain had a very high peak in spring. Italy too. Portugal was continuing to rise. So you can see here that Germany fared relatively well in springtime with their restrictions. So I would say this was an example of very successful measures. Down here you have South Korea. So South Korea is for me also more how you can even do it better. So they were very strict in tracking any new corona cases. And in this way they were able to keep it at a very low level. So I find that actually quite impressive, and this is also a role model on how to deal with the virus. Yeah. So as a comparison here, the 7-day incidence. So we saw I used the 16-day incidence for my estimation of the concurrently sick. In recent months, the 7-day incidence is used more widespread and per 100,000 inhabitants instead of 1 million. And the 7-day incidence is used for defining new levels for measures. So that's why I plotted here. So here you can see the 7-day incidence. So for February 13, we now have a 7-day incidence per 100,000 people of 62. So that's actually a good number. And you can also zoom in here and compare it to the spring numbers. So you can see in spring, here we had, at the peak, we had 49. Right, so actually we are still not at the peak of the spring. So that's kind of interesting, because the spring was kind of bad already, but we just reached 50 then. And we are still at a much higher level now, at 62. And at the peak, we had about 217. So a lot higher. So let me go back. Yeah, and also Portugal is impressive. In its peak, it had 817, so 70. Quite impressive. And it was very successful combating it. So now it's down at 215. Also the US at its peak had 500. So that's also extremely high. But since mid-January, they're very successful combating it. And now they are down at 200, right? So they are also now very successful since mid-January in combating the virus. Similar Spain. It's kind of interesting that Spain had a similar peak as the US, and now it's going down a lot. Also to about 200 here. And compared to South Korea, they have 5. So this is where we want to be, where South Korea is now. Yeah, interesting is also the computation of the underdetection rate. So this is actually the difference between the number of detected and the real number of infected. Or I should say the ratio, not the difference. So the underdetection rate takes into account how much testing is done, including its accuracy. It is an estimate of how many more true infected there are compared to the detected infected. It is computed as the ratio of the case fatality rate to the infection-based fatality rate. Right? So you have a certain number of detected, and a certain percentage of those detected will die. So there you have a percentage for that. But then you can also estimate how many of all infected people die, and that gives you a different percentage, right? And this infection-based fatality varies depending on the age of the people. So depending on which country and which average age that country has, this infection-based fatality rate differs. So in relatively old countries like Germany, this will be higher than in relatively young countries, say like Lebanon. So I assumed 2% here because that fits to the data that are observed. So see, for instance, my Corona update video where I estimated it. So this can differ somewhat between countries depending on the average age of the population and also the health system. So the 2% is a more or less rough estimate. Keep in mind that it can also be a factor 2 larger or smaller. So this is now a very rough estimation. Right? It's not very precise. A factor of 2 is always something that can happen or that should be kept in mind. That is very inaccurate with this factor of 2. Yeah, so the case fatality rate is computed as the number of deaths divided by the number of deaths plus recovered. Right, so this is from the people that you detected. And then you can basically divide this, make this division here, and you get the underdetection rate. Yeah, so for this computation, I'm using the accumulated data to obtain more stable results. This works only for countries who report the number of recovered. That's the problem for countries like Sweden, which don't report it. Here I just have to use this 16-day incidence, which you can see here instead, which makes it again a little bit less accurate. Yeah, but still I can make a rough estimate about the underdetection rate, which gives me a ballpark figure, so that I have a rough estimate how many infected people are there really. So here you can see the computation for the different countries. So again, Spain, France, and the US, I used the 16-day incidence for the number of recovered or death. And these are the underdetection rates. And I found this actually quite interesting. Even keeping in mind that you easily have this factor of 2, the shape gives you some interesting information. It shows you that in the beginning of the pandemic, this rate was very high, as expected, because they still needed to roll out the testing. So also in Germany here we started at 15, and then actually quite quickly in Germany in March we went down to about 2.5, 2.4. So here in Germany we rolled out testing quite quickly. That was somewhat different here in the US. So the US started very badly and then also improved also only very slowly during the summer. Right, so that was not so good. Italy, similarly, they only had a very slow improvement for testing. France, quite similarly, also Spain, they were a little bit better. So you can see the different shapes here of those southern European countries, and also the US compared to Germany, which rolled out testing very quickly. So that was actually quite good. Also, when you compare it here to South Korea, so they started also quite high at 24, and then actually even earlier here, like in beginning of March, mid-March, they reached very good testing. So now they went down to 1.3. So they even have better testing than we. And actually, I think in South Korea, they developed the first corona tests. So they knew it was very important, and that's why they put a lot of effort into it and applied it very successfully. Yeah, and using this underestimation rate, we can now estimate the true concurrently sick. We just multiply the concurrently sick by the underdetection rate and get the true concurrently sick, and that's this curve here. So this now takes into account the different underdetection rates. But you can see it doesn't really change so much. You can see actually that Italy now sticks out, right? They have very high numbers and also high underdetection rates, so Italy really sticks out here. Portugal, yeah, it's like before. Here the US is very similar. Yeah, so that basically shows that most countries have good testing now. In the US, actually, you get much worse numbers here in the beginning of the pandemic using this underdetection rate. So this is from all the countries which had bad testing in the beginning and slowly ramped up. You can see that the spring numbers here are actually much higher. Here Portugal had very high numbers in the spring, but they didn't really detect it so much because of bad testing. Here, when you look compared to Italy, the spring numbers were almost as high as the fall numbers, right? And you can see the US, also the US. Here the US actually had much higher spring numbers here than now in the fall, which is kind of interesting. So taking into account this estimated underdetection rate, for the US, it looks like the spring peak was higher than the fall peak. For us, it's different. So for us, we actually have still a lower spring peak than fall peak. Yeah, then we have the resulting accumulated death cases per million inhabitants. That's also an important measure because we can see the effect on society, the fraction of people who died. And here we can see Germany now has 780 people from per million inhabitants died. And we can compare it to the US, which have 1,400. So that's about twice as many. So the effect on society in the US is about twice as much. Right. Similar Italy. Italy has a similar rate. Spain and France. So it's kind of like the southern European countries have a similar effect on their countries. And then Germany is about half as much, and then here South Korea is only a fraction at 29 people dead from corona per million inhabitants. So that also shows the success of the measures, right? You want to be down here. So South Korea was very successful. Germany was still quite successful, but then southern European countries and the US were not really successful, right? Yeah, and it also shows that the right measures really make a difference. They make a difference between life and death, right? So it's something to take seriously. Yeah, so then I have this comparison to influenza, to the flu. So for the flu, often you read about the excess mortality of a heavy influenza season. And I looked it up and I found a heavy influenza season has about 200 deaths per million inhabitants, right? But these also include other causes of death, for instance, traffic death. Could also be that in that year you had a very bad weather and you had a lot of people dying in cars. Here's my source for it. But the confirmed influenza death, so those people who really died with this virus, with the influenza virus, is just 20 deaths per million. So this is not excess mortality, but really confirmed death. So these are the confirmed influenza deaths. Here I have my source. And for COVID-19 death, we always list the confirmed corona death, right? So this is actually the suitable comparison, 20 deaths per million. Right, and remember now we are at 750, so much more than influenza. Yeah, so Germany and the US already surpassed these 20 deaths per million in early April. Right, and also keep in mind that for influenza we have vaccines, so everybody who wants to can have vaccination, which is only coming up for corona. So I think once we have the corona vaccinations, we don't need lockdowns and measures anymore because anybody who wants to can take a vaccination. And those who don't take the vaccination, they do it on their own risk. Yeah. So for the death cases, I also have a model. So you can again use this logistic model. I took the same logistic model just with the numbers for the death, and here you can see the plot. So here the blue one is from my logistic model, and the orange one is the actual data. And you can see here in March we had this jump from this spring peak, and then we had those the corona measures, and you can see it flattens, so it now runs more or less parallel to my model, so that's good. But then here again here now in late October we have a steep increase in the number of death cases, and that's because of the increase in corona infections that we saw in early October. So we have this delay of about 3 weeks until those people die. So here you can then see this steep increase, and now it runs more or less parallel to my model. Right, so not too much change actually. And there's maybe a slight flattening here at that point, which is hard to see, but more or less still runs in parallel. And it would be nice if you get it maybe coming closer to my logistic model here. It would still be nice to come closer to this model. Yeah, but more or less it shows that we are now on the right path, and still hoping for and waiting for the vaccines. Yeah, so we are just before 800 deaths per million. Remember, influenza was about 20. Yeah, and to see the trend or forecasting, we need this increase factor of concurrently sick. Right, so that's my day-to-day increase factor for my model, and that shows us if we are on the right track. So this is actually quite a sensitive measure, which shows if measures work, and also allows us to make a prediction, assuming that we have the same factor. So we can say if this factor stays constant, then how does it continue? So for analysis, we can calculate the increase factor of the concurrently sick as a quotient of the numbers for 2 consecutive days. This quotient is the same for the absolute numbers or for the number of concurrently sick per million inhabitants, because we divide. It is related to the reproduction factor, but not the same. So values greater than 1 means an increase, less than 1, this is where we want to be, a decrease, and a constant factor means a constant value above 1 means we have an exponential growth similar to a fire that spreads. So actually we don't really want to be above 1. This increase factor is almost the same for the true concurrently sick, since the under-detection rate only changes relatively slowly. Because this varies weekly because of the weekends, the following plot shows 7-day averages. So I computed this ratio, but then averaged over 7 days because of this weekly fluctuations of case numbers. And here you can see the result. So again, orange is the numbers from Germany. And you can see here this peak is basically coming from this artifact where we had this data inconsistency, where basically at one point data was delayed. So ignore this part. The curve should actually continue on this path here. And you can see here that in mid-December we had a factor of 1.016. So this actually corresponds roughly to my model. But then in after Christmas it went down. So you can see after Christmas went down, then went up again here around New Year's or early January. Then went down again, and now we are at 0.98. So now we are below 1. So here we have the 1, and this is where we want to be. Right? We want to be below 1. Compare that to South Korea. So they are always hovering around 1, sometimes above, sometimes below. But they manage to keep it mostly below, and that's the important part. Right, that they don't have this exponential growth. In Germany, we had too long a, let's see if I can scroll it here, auto scale, yes, so in Germany, like here you can see it from the beginning, from March. Here in the beginning we had very high increase factors, 1.3, way too high. And then in April we managed to go below 1. And then here in the summertime, you can see here, July, it went up, 1.03. Here it's reaching 1, then it goes up again, and then particularly early October it went up a lot, 1.07. So this was bad in early October. And then here, November, it went slowly down, then in December it went up again. Here we have this artifact, and here since December we have more or less factors of below 1. You can also compare with South Korea. So they also had their peaks here, but they quickly went down again, right? So they managed to keep it down. Here they went up and they also went down again. You can also compare it to, say, the US. Here you have the US, the United States. So they stayed just above 1 most of the time, and that's something you don't want to have. You want to be below 1 most of the time to keep it in check. Yeah, so you can see also the difference between the home button and auto scale. Auto scale takes all data, and the home button takes a preset which I programmed in my program. And actually you can see the Python code if you click on Form and click on Show Code. So here you can actually see the Python code, and in Colab you can actually also modify it and to adapt it to your needs. Yeah, so hide code. So that's very practical, and that also allows all the functionality that you can see here. So here now I was hiding the form. You can see the code, and form, hide code. Here we have the plot again. Yeah. So here, observe in my video from March, Corona special, I found we need an increase factor of 1.02 to make it sustainable until spring of 2021. And we indeed reached precisely this factor in Germany most of the year 2020. But late in September it started to increase again, right? That was a problem. So we can now take this factor for prediction, right? So here I now have a prediction, and you can actually set the number of days you want to do a prediction using this slider here. So it takes the latest numbers. So here, the latest numbers from February 13th, and just keeps the increase factor constant, and then makes the prediction over the next 35 days. So here you can see it. Here we have Portugal, so it's on the way down. That's good. Germany is also on the way down. Here, South Korea is kind of flat, which is good because they're very low anyway. Also the US is going down. France is going down, but not so fast. Similar, Italy. So actually the trend is right. This is where we want to be. Yeah, and then you can do the same with true concurrently sick. But yeah, this is the true factor that you want to have. But it basically, as mentioned, gives us the same information because we don't have much change in the testing. If you would have change in testing rates, we would see it also here. Yeah, and that leads us basically to the happy end, the vaccinations, right? So here I have a website for the vaccination rates. And you can see here, when you scroll down in this website, yeah, so you can see here the vaccinated per 100 people. So this is basically the percentage. Israel is already at 70%. So they're pretty much done already. Then you have the United Arab Emirates, 50%. They're almost done. United States is currently at 15%. So it takes them, say, 4 to 5 more months to be done. And in the EU, we are at Here's the European Union, 4.7. So it's like 5%. But it's expected that we ramp up the speed of vaccinations. And then it looks realistic that basically we are also done with vaccinations, say, until the end of summer. So I would guess until the end of summer we are done with vaccinations, such that everybody who wants can have a vaccination. And that's the important part. Let's see. Yeah, so you have slightly different data points here. Also, what I also found interesting is instead of per 100 people, the absolute numbers. And then I take a table and say absolute change. So that shows you that here in the world we already have 170 million vaccinations. So it's actually kind of amazing how many vaccinations they were able to make in this short time. So it's just 1.5 months. In Asia, they have 66 million, United States 50 million, North America about the same, then Europe 40 million. So you can see actually the number of vaccinations in the United States and Europe is very similar. Then we have China. China has a much larger population, but actually has much fewer vaccinations, or somewhat fewer. Then the European Union has 20 million, so this is just the European Union. And here the United Kingdom has 15 million. So they started earlier. They already started in mid-December, so that's why they had a head start. Let's see, Brazil is kind of low. Germany has a lower population than Brazil, but it's so in comparison it's actually better. Russia now has 4 million. So Russia is kind of surprising because they have a relatively small population of 140 million, so much less than the EU or Europe, but only 3.4 million vaccinations, even though they started much earlier. So I found that kind of surprising. So it seems they have problems manufacturing their vaccine. Yeah, so it's kind of an interesting table, and I think this table shows that there is a lot of progress with vaccines. So despite all the criticism of it being too slow, I think it is actually, when you look at this number, 170 million worldwide, it's amazing speed. And it's expected to more than, the speed is expected to more than double in the coming month. Okay, so on this hopeful note, I want to end this presentation. So thanks for your attention, and then see you next time.